Hello, this is Satbir. The topic of our discussion in this video is second order linear differential equation with the constant coefficient. In the classification of the differential equation, these differential equations are ordinary, higher order, and they are linear. Second order differential equation has this general form, which is a function px times the second order derivative of the function y with respect to x plus another function qx times the first order derivative of the function plus third function rx times y is equal to gx, where the function px, qx, and rx and also the function gx, they are all continuous. In this video, we will consider one particular case of these differential equation where we will take the function gx is equal to 0 and also the coefficient of these differential equation, which is a px, qx, and rx, we consider them all constant, or in other words, they are all numbers for us. Such differential equation are called homogeneous linear differential equation with a constant coefficient. So here are the few examples. For y double prime plus 3y prime plus y is equal to 0. So this differential equation is written in a Lagrange notation. All the derivatives are written in a Lagrange notation. And this is another example of such a differential equation. And you can also consider this differential equation to be a second order linear homogeneous differential equation with a constant coefficient. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Next, we will learn how to find the general solution of these type of differential equation. To find the general solution, we are looking for a function y such that a constant time it is second derivative plus another constant time it is a first derivative plus a third constant time function itself is 0. We know that the exponential function y is equal to e to the power some constant time x has this property. If I calculate the first derivative of this function, it is constant time the function itself. Even if I calculate the second derivative of this function, it is another constant, which is r square time the function itself. So if I plug the second derivative, first derivative, and the function y itself in this differential equation, I will get this quadratic equation. Or in other words, when I will solve this quadratic equation will give me some values of r. And when I plug these values of r back into this function will satisfy this our differential equation. Or in other words, this function will be a solution to our differential equation. This quadratic equation, also known as characteristic equation, or also auxiliary equation. The form of the general solution of our differential equation will depend on the nature of the root of this quadratic equation. So if case number 1, if the characteristic equation has two distinct roots, then our general solution of the differential equation will look like that, which will be y is equal to some constant c1 e to the power first root time x plus second constant c2 e to the power second root time the independent variable x. If we have a repeated root, let's suppose r is equal to r1 is a repeated root, then the general solution will look like y is equal to c1, the first constant time e to the power r1x plus c2, now the x, there is a x extra x, which is an independent variable, times e to the power r1x. And if the characteristic equation has a pair of imaginary root, we also know that when a quadratic equation have imaginary root, they have always occur in conjugate pair. So let's suppose our root is alpha plus iota beta, I time beta, then the general solution will be e to the power alpha, which is the imaginary part of our root, then parentheses c1, a first constant time cosine of the imaginary part of the root, plus another constant c2 sine of then also the imaginary part of our root time x. So this will be our general solution. Let's consider a few examples and practice this method on them. So my first example is my differential equation is y double prime plus y prime minus 6y is equal to 0. The first step of my solution will be to calculate the auxiliary equation. To find the auxiliary equation, or in other words, the characteristic equations, you turn the y double prime to r square. You turn this first derivative to r and the function y to r to the power 0, which is 1. So I substitute these value in my differential equation. So it will become r square plus r minus 6 is equal to 0. So this is my auxiliary equation. In step number 2, I will calculate the root of this auxiliary equation. So there are two ways to calculate the root of a quadratic equation. So you can use the quadratic formula or you can also factor. I will factor this quadratic equation here. So the factor of this quadratic equation will be r minus 3 and then r plus 2 is equal to 0. Therefore, the root of this quadratic equations are 3 and negative 2. Since I have a 2 root and they are also different, so I will use the first case, which I showed you in the previous slide, to write down the general solution of my differential equation. So my general solution will be y is equal to c1, a constant, e raised to power the first root plus c2, the exponential function of second root time x. So this is the general solution of my differential equation. Let's take one more example. Here in step number 1, we will again calculate the auxiliary equation. To find the auxiliary equation, I will turn the y prime to r square. I will turn y to r and y to basically r to the power 0, which is 1. I will substitute these values of the derivatives into my differential equation. So this will become 4r square plus 12r plus 9 is equal to 0. Now you can either factor or use the quadratic formula to find the root of this quadratic equation. This time I will use the quadratic formula. So my root will be r is equal to minus 12, which is a b, plus minus b square, means 12 square, minus 4ac, divided by 2a, 2 times 4. Next we will simplify. So 12 plus 12 square is a 144 and 16 times 9 is again 144 divided by 8. So therefore this is a 0. So it's going to be a 12 divided by 8, which is same as 2, and that will be go to 3. So this is a 3 divided by 2. So as you can see that in this case, we have the repeated root and both root r is equal to negative 3 divided by 2. So to write the general solutions, I will use the second case, which is the case when we have the repeated root. So step number 3. In step number 3, we will write the general solution as y is equal to c1 e raised to power minus 3 half x plus c2 time x e raised to power again 3 half x. So this is our general solution of our differential equation. Let's consider one more problem. Here I have a differential equation y double prime minus 6y prime plus 13 is equal to 0. So again, same as in the previous example, I will calculate. First, I calculate the auxiliary equation or a characteristic equation. So the auxiliary equation of this differential equation will be r square minus 6r plus 13 is equal to 0, because I will turn second derivative to r square, first to r, and the function y to 1. And in step number 2, I will find the root of this characteristic equation. This time again, I will use the quadratic formula. So this will be a 6 plus minus b square 36 minus 4ac 13 times 1 divided by 2a. So if I simplify this expression, so I will have 4 times 13. So 6 plus minus 36 minus 52 divided by 2. Or in other word, 6 plus minus negative 16 divided by 2. So since there is a negative in the radicals, I will pull out as a I. So this will be a 6 plus minus I times 4 divided by 2, which I can further write 3 plus minus I 2 times. So these are a complex root this time, and it is a occur in pair. So 3 plus minus 2i. So this time I will use my third case when the root are complex. So to write down the general solution of this differential equation, I will write it as e to the power, first the real part. The real part of these this pair is 3, so 3x. And then parentheses, constant c1 cosine of then the imaginary part of this root, which is a 2 times x plus c2, then sine, the inside of the sine will be the again imaginary part of x. So this is our general solution of the given differential equation. And that was the case when you have imaginary root. Here I have one more quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video. Thank you very much for watching. I will see you in the next video. Bye for now.